This is lecture 8B on the hydrostatic pressure on horizontal plates. And now we're going to do two types of problems of hydrostatic pressure. One is the force and pressure that are acting on a flat horizontal plate. This is a horizontal plate buried under or lying at some depth underneath some fluid. The other harder problem is that of a vertical plate. So let's look first here at the easy problem, which is a horizontal plate. And as before, we have to make a sketch. So the sketch here is that you have some object here, and I'm going to look at the side of it. That's my object right there, and it is lying underneath some fluid. Okay, now I'm going to add a coordinate system to it. And here's what I do. You're free to do what you want to do, but I like this. Okay, and here's my x. Okay, I put the origin of the coordinate system here right where the object is lying, so that when I say, for example, the pressure, here's a circular plate lying under 25 feet of water, then when y equals 25 is right here at the top of the water level, and the object is at y equals 0. So in this problem, I want to calculate the force on this object. It's lying under 25 feet of water. First thing I do is calculate the pressure at that depth. Where pressure, I'm going to get the pen here. Pressure equals gamma times d. Okay, gamma is the specific weight of the water. Specific weight of water is 62.4 pounds per cubic foot. The depth is 25 feet. So here's my 25. That is the pressure of the water at that depth. Force is pressure times area, so I need the area of the plate. It is a circular plate. It's got a 9-foot radius. Well, we'll fix this up. It's got a 3-foot radius. So then the area is pi r squared, which will give me 9 pi feet squared for the radius of the plate. Then the force is pressure times area. So our pressure was 62.4 times 25 times 9 pi, and that gives me about 4,500 pounds of force on that plate. Just for a little bit of clarity, although I can't draw very well, and here's the circular plate. So by calculating the force, then I'm adding up all the pressures that's being exerted on this plate. And all the pressure is equal because every piece of this horizontal plate is lying on under exactly the same amount of water, which is calculated here is 62.4 times 25. So the pressure on each point within this plate is the same. So the force is just the pressure times the area. Okay, sorry about that error here. That should have been a 3-foot radius. Let's do a couple more calculations just for examples for the same basic idea. Here we're going to have a rectangular plate. It's going to have a width of 2 centimeters and a length of 5 centimeters. It's the bottom of a 20-meter tank, oil tank. And we want to know the force on this plate. Okay, so we have the same, it's basically the same idea as before. I'll start here. The force, wait a minute. Force is pressure times area. So I need to find the pressure and I need to find the area. The pressure is going to be the pressure of the oil at that depth. I need the specific weight of the oil, which is 8,950, and this would be newtons per cubic meter, times the depth, and the depth is 20 meters. So I'm going to multiply those together. My units are newtons per meter squared, which is units of pressure. Right? So again, gamma D. Gamma is the specific weight of the fluid. D is the depth at which the object is submerged. Right. Now I need the area of the plate. The area is, of course, I have to use right units. We've got 2 centimeters times 5 centimeters. Okay, 10 to the minus 3 meters squared. I multiply those together and I get a force of 179 newtons. The sketch, of course, is just the same as the other one. Let me get here. And I've done, here's my y-axis. This is 20 meters. And here I have this little rectangular plate. Of course, I said do the sketch first, and now look at me, I'm doing it second. Okay, here's the pressure due to that water. It's acting on every single little area of that plate, and it's the same at every point. The pressure is 8,950 times 20 newtons per square meter, acting on every little piece of that plate. Okay, we take the total area of the plate, which is 10 to the minus 3 meters, multiply them together to get the force acting on the entire plate. This next calculation is just for fun, but there's a rule of fun in scuba diving that for every 33 feet underwater, the pressure increases by 1 atmosphere. And let's verify that this is true. Okay, here is 1 atmosphere, 14.7 pounds per square inch. That's pressure. Okay, this is a unit of force per unit area, hence it is a pressure. So let's calculate the pressure under 33 feet of water and see if it does equal 1 atmosphere. So to calculate the pressure under 33 feet of water, we multiply the specific weight of water, which is 64.2, this is pounds per cubic foot, times the depth of 33 feet, and we get 2,118.6 pounds per square foot, units of pressure, which is force per unit area. Right? Now we have to convert square feet to per square inch, and we end up with 14.7125 pounds per square inch for under 33 feet of seawater. Note here that I used the specific density of seawater, which is 64.15. Okay, so we verified the rule of thumb for scuba diving that for every 33 feet of underwater, you can add, you can assume that you've got a pressure, an increased pressure of 1 atmosphere.